Okay, so hello everyone. Welcome to our Hangout for the Data Science in Stratified Healthcare and Precision Medicine course. This is our Hangout for May 2019. So my name is Arati Manataki. I'm one of the course organizers. I'm here with Alex Szybilski.
That's right. Hi, I'm one of the teaching assistants on the course.
And we are delighted to have here today with us a medical imaging expert. So let me introduce Dr. Georgios Papanastasiou.
Hi everyone.
So the plan for the session is to just remind ourselves what the course is about, what is going on in the discussion forums, and then really we'll move straight to the interview with Georgios.
Mm-hmm.
Georgios or George?
Either way is fine.
Okay.
Either way is fine. Georgios is the Greek one.
Okay, I'll go for Georgios. So what is the course about? Remember, this is a 5-week course introducing different types of data science techniques and ways of working with data in the health sciences. So I know there's people attending or joining the course at different times. So the idea of saying, oh, you're all now in week 3 is not that relevant anymore. So I'll just go through different topics that we see in the course. Also, just so you know what the course is about.
Absolutely.
Give you an idea.
That would be very interesting to me.
So we start on week 1 with an introduction to what precision medicine is and what data science is, what stratified healthcare means. And we move on to a very short introduction to programming in Python. So this is a course where there's a little bit of a hands-on element. People have a go at doing some simple but representative tasks in health data science.
Absolutely.
Using Python. So we move on to week 2 to look at sequence processing and medical imaging and image analysis. And perhaps it's worth talking a little bit more about topics that we see in that area, since we're going to be discussing about medical images.
I'll be pleasure.
So we look at different medical imaging modalities. So we look at X-ray, CT scanning, MRIs, PET and SPECT.
Mm-hmm.
We talk about differences between them and which ones are used for different types of analysis goals, let's say. So physiology versus anatomy. And then we move on. We also cover different types of how you can capture imaging data. So we talk about the DICOM format. Very important. Which is a standard in the field, right?
Absolutely. It's very standardized, yeah.
And then we move on to different techniques for analyzing medical imaging data. So we look at pre-processing. That includes enhancement or feature detection in clinical images. We talk about segmentation, so how we can identify different parts of a medical image. And we talk about particular techniques there as well. So we cover thresholding, region merging, and region growing. And in fact, we look at region growing in one of the programming tasks that we have in week 2 to do with analyzing medical images. And then another type of image analysis that we cover is to do with registration. So for combining different images or for comparing 2 different images. So for instance, before and after treatment. And that's pretty much it, really, for when it comes to medical imaging. We look at different types of data in the health sciences, like natural language data, so text. So one of our programming tasks is to do with analyzing clinical notes or a biopsy report. And then we look at other types of modeling methods, network modeling, process modeling. So in network modeling, we look at, we talk about applications in biology, while in process modeling, we look at applications in healthcare and pathways of care for patients with different conditions. And on week 5, we conclude with, basically, we bring everything together by looking at integration and linking of data, and we talk about a different approach to representing data. So in terms of graphs, so graph data, we talk about advances in semantic web technologies, so RDF and ontologies. And we talk a little bit about ethical considerations, legal considerations, and implications for society. And I think it's week 5 where we have a project for you to work on that is assessed by your peers. So yeah, that's pretty much it when it comes to the different topics covered in the course. I think I will now move on to Alex and discussions that you might have seen in the course.
Yeah, so I mean, there's more and more people joining the course, which is great, and also some people participating in the discussions forum as well, so answering other people's questions, which is really helpful. Mainly, there's been more programming questions, so people asking mainly at points where you get stuck, for example, the programming task, where to find help or references. So I think that's a common problem, but actually it's now there's so many resources for programming. It's really easy to use the forums or the online forums and some other links that I've been posting in the discussions forums that are really useful.
So I've noticed you recommended Stack Overflow.
Yeah.
What is Stack Overflow?
So it's probably the largest programming online forum, and it's not just for Python. It has many different subsections for different programming languages, and there anyone can really post a question they have or a problem that they're struggling with, and there's a great community that will help you answer that question. Most of the time, any problems that you may have are probably already answered, so it's really useful to just have a look, have a search.
Mm-hmm.
Yeah. There was also a question about whether there's a capstone assignment as part of this course, and given this is not a specialization, there isn't one, but there is, as already mentioned, the final assignment, which is the report, and which is peer-reviewed. So I think the requirement is to peer-review 3 other assignments and submit yours.
So let me just say that this is at least 3. So if you feel like practicing a little bit more and finding out more about the work that your classmates have been doing, feel free to go ahead and assess even more. 3 is the minimum, so that you can see the feedback that you got from your classmates. So you won't be able to see your mark until you've assessed 3 projects. I've seen that there's been quite a few posts from people asking for their classmates to review their assignments. So I think that's a great use of the forums, to be honest. If you're still waiting for someone to review your assignment, feel free to post a message in the forums, and anyone that is out there, feel free to coordinate to assess each other's work.
Yeah.
And so when announcing this Hangout, we asked our learners to post any questions, any new questions that they might have for us to discuss. So was there any question in the forum?
Yeah, so there's one a really great question asking about the regulatory requirements of AI systems within clinical practice. So firstly, the question asks in terms of error fixing and code testing, how these systems can be properly tested before they are put out into clinical use. And secondly, also, when these tools are deployed in clinical settings, who may be liable in cases where the results of the algorithm may end up causing harm to the patient. So I think quite a difficult question, and definitely a area of a hot topic, area of a lot of research and debate right now. In terms of the code testing and the errors, the actual machine learning algorithms, the question mentioned SVMs and neural networks. These are formal algorithms with mathematical proofs behind them. So there are established ways of implementing these. So there are definitely ways of properly testing that the implementation is correct. And so any people that do implement these, whether they use existing packages or libraries, these should be properly tested and well established. In terms of whether the actual results of these algorithms, I think validation is a huge part of the development of AI in these settings. So I think it's also a major challenge. Having access to the different data sets, which would allow you to properly validate the algorithm is definitely a challenge. And make sure that your system is generalizable to different settings and different types of patients that in the end it might be used for. So I think that's definitely a challenge. Regarding the second point, in terms of who might be liable in cases where something goes wrong, there are many proposed ideas currently, and we will link some interesting papers after this YouTube Hangout. So there are ideas regarding considering the AI system in terms of personhood. So the AI system itself would potentially be insured by somebody, and in the case that a case would be brought against the AI system, or a result that a decision was made based on the AI system, the insurance would actually cover these cases. There are also ideas that all groups involved in the implementation of the AI system and those using the AI system should be responsible, so there should be shared responsibility. But I think definitely there's a duty to validate these systems before they are used, and this is still very much an area of active debate.
And in fact, I think it would be worth taking the debate to our forums as well, because I mean the community has not reached any conclusions yet, and there are different points of view to consider. So perhaps what we could do is create a new thread in the forums to have people discuss exactly this question, which we thought was brilliant.
Yeah, that's good.
And you said there are some papers that you're gonna
definitely.
recommend?
So we'll definitely post some references, which I think should be interesting.
Amazing.
Yeah.
Great. Thanks. Right. So I think now is the exciting moment of getting Joris in the discussion. Well, it's more exciting for us.
Okay. Glad to hear.
So I have to say that medical imaging is one of the areas I knew fairly little before developing this course. And it was through reading and discussing with colleagues that I thought, wow, there's something really cool going on here. And last year, so there's a big AI conference, Triple AI, and I was reviewing papers for Triple AI with applications in. So it was about clinical applications, so biomedical applications. And 4 out of the 5 papers that I got to review were in medical imaging.
Right.
So that, I think that just goes to demonstrate how much progress there's been lately in this field.
Absolutely. I think that's a breakthrough, as you say. I think what makes fascinating medical imaging is the fact that you can see inside the body, and without medical imaging, you can't really understand things that of the physiology or sometimes of the diseases that happen inside our body. So we use the term in vivo. So we can understand what happens in vivo, in real living tissues, without interrogate, without invasively affecting the tissues, just leaving them how they live inside your body. There is a huge progress over the last few years. I mean, the last possibly 30 years, maybe more, maybe 50 years, but the last 30 years and maybe even more the last 15 years, there is a huge progress in terms of how we optimize these techniques to make the data more ready for analysis. So in the very beginning, possibly the first generation of the images, you could extract less information, let's say, because of many reasons, because the science, the physics that are used to make an MR image or a positron magnetic resonance image or a positron emission tomography image were different, and there was a huge progress in the physics. But at the same time, people realized that the images need to be analyzed, not only to be investigated by a radiologist or a clinician. So this analysis that possibly is very relevant to your audience today is what really affected the way and had a considerable impact on the way we perform medical imaging technique in terms of the experiment.
So by analysis, you mean computational analysis?
Yes, we mean image analysis because your data are images, which means are pixels, pixelated information. And always the last part of this image processing is computation, which means you want to derive some physiology, patient-specific information about the specific cohort you analyze. Let's say if it is for a heart problem, or for a liver problem, or for a problem in oncology. Yes, and so this analysis actually made the community to realize what you can really extract from these images. And there was a second generation of medical imaging techniques that they did not only involve extracting the images from the data, but also extracting maps from the data, which means quantifiable information of, let's say, as you said before, you gave some examples of the anatomy. So you want to see whether a tumor has enlarged, let's say, in oncology, or you want to go into more detailed information about the pharmacokinetics of the tumor, which is one of my areas of expertise.
Okay, so what is pharmacokinetics?
It actually comes from the pharma, which is the drug that you inject into the patient, which is a tracer. Although there are some attempts to also trace a drug passing through the tissues, and comes also from the second term in the word is the kinetics, which means how the tracer is passing through the body and through the tissue. So one very distinct area of medical imaging, which is actually part of the future of medical imaging, is called dynamic imaging, which actually you inject a tracer independently of whether it may have to do with MRI or with PET or with SPECT. A bit more with MRI and PET, these applications are, where you inject a tracer and you acquire images very quickly over time, and you try to understand how the tracer passes through an area or an organ inside our body.
And what would that tell us? What would that tell the clinician, for instance?
This could say information that you cannot otherwise extract. One very characteristic example is the fact that you can quantify blood flow. Imagine that you can't really quantify how the molecules of your blood inside the arteries, the speed of the molecules. You can't really quantify this by sitting right here. But by performing dynamic imaging and analyzing the images with pharmacokinetic models, you can approach measures of blood flow, which means how quickly the flow is running through the tissue. And this is different from organ to organ, and different from healthy to pathologic areas.
If you were, say, to study blood flow or study, I don't know, something to do with the lungs, with pharmacokinetics, would you be would you go for different settings of speed, for instance? Is that
yes,
the idea?
Yeah. That's a very you try to approach many details that have to be put in place in order to make this protocol analyzable.
Right.
So, for example, you want to acquire very quick images in MRI. So you need to make a very clever way. You need to convince your protocol to acquire quick images without losing spatial information.
Right.
And that is not only involving mathematical knowledge and knowledge of the physics, but also it came as a result of the very important evolution of the detectors and of the hardware of medical imaging techniques. So these things came together.
Yes.
The analysis progression with software progression are two things that are coming together, and they aim towards improving these medical imaging techniques, as you said, make more quick images, but at the same time without losing information, either spatial or temporal. So the more information you have in these images, the
Yeah.
better for the analysis, because you can get more clever models, more detailed models. Although as modelers, you may be trained to keep your models as simple as possible. That's possibly one of the principles of modeling. But at the same time, having more information into your data means that it gives you flexibility as a modeler to extract more information and develop more clever and detailed models.
I see. Now, you mentioned advances in hardware going hand in hand with advances in computational methods. So I'm wondering, are these two separate communities? And if they are, do they meet enough? And how does that work?
That's a very interesting question. Because until today, although these huge advances in medical imaging, these communities are a little bit separated, I would say. So someone who does computational analysis cannot really understand many things about the detectors. Or the people who do the detectors cannot understand the software, the analysis domain. So there are conferences in place that they try to deal with these differences in the knowledge and in the domains and bring the gaps. So there are almost all the international meetings of magnetic resonance imaging and positron emission tomography imaging and SPECT, single photon emission computed tomography. They all aim towards bringing this gap. I mean, the technical meetings.
Yeah. And which community do you fit in, would you say?
I would say I am quite flexible with the communities. I would say that I like quite many. I mean, there are three main possibly communities: the MRI community, the CT community, the computed tomography community, as well as the molecular imaging community. Although there are approaches to perform molecular imaging with MRI nowadays, the most traditional molecular imaging techniques are the PET and the SPECT. So if we could divide these three communities, there are conferences that try to combine things. Although these communities are separate still, there are very serious efforts to make more communication across the communities and make things interact more and more.
That's reassuring.
Yeah, and obviously analysts, which is the next generation of people who are going to join in, I think they will be benefited from these interactions. And the field, medical imaging is evolved, but also the interactions across communities is evolved. And I think that's a very positive thing. Although difficult sometimes, it's very positive.
So you do research in the University of Edinburgh, right?
Yeah.
So would you like to tell us a little bit about a project that you've been involved in, just to give our learners an idea of what kind of research people do and what is what is current?
Absolutely. Yeah. In the past, I have worked a lot in pharmacokinetic models, as I said before. I did my PhD in cardiology, where I worked. I was working on dynamic imaging using MRI, and we were injecting a tracer to healthy people as well as to patients. And through pharmacokinetic model analysis, I was aiming to stratify which patients they have reduced blood flow because there was a stenosis in very tiny arteries in the heart that feed blood to the heart, called coronary arteries.
Okay.
And these coronary arteries, if they have a stenosis, they can cause a very serious heart problem called myocardial infarction. So being able to non-invasively detect this problem, it would revolutionize the field because it can non-invasively stratify these patients instead of inserting cameras,
of course,
which is very terrifying for lots of people. That's what people do nowadays as the gold standard. And the results were really good, which was very encouraging for me to continue. And now I'm working in dynamic and pharmacokinetic analysis for brain applications, for people who have dementia. One of the projects I am working on is to try to detect It's called cerebral amyloid angiopathy. It's a protein that's called amyloid accumulating in the brain, and people think that the hypothesis there is that it causes brain strokes. And through this pharmacokinetic model analysis, it is possible to quantify this amyloid accumulation in the brain, as well as to see whether this is causing other differences in brain tissue, such as blood flow differences, or whether it causes differences in the permeability of the vessels, and go into more and more detail. So obviously this pharmacokinetic model analysis that I discussed a lot about today is involving physiology-based models, which require some knowledge about the biology that you investigate,
right,
as well as the clinical question you want to address.
okay,
So you want to keep them as simple but as descriptive as possible at the same time. But they all try to maintain some information about some assumptions and some a priori knowledge about how the blood flow is occurring, let's say, through the brain. And obviously, a new project that I work on, I will start working actually on this summer, is involving machine learning in medical imaging, which is again hopefully relevant to your audience. That actually I will be working on devising machine learning algorithms from MRI data to investigate a quite unexplored field, which is fat accumulating in the body through MRI images. And the aim there is to see whether this fat is active and plays some kind of metabolic role. It affects other diseases. It can be the cause, or it can be associated with other diseases. And now we discussed about pharmacokinetic models and, let's say, anatomical information from these images, etc. Now we move towards, with machine learning in medical imaging, I think we move towards more data-driven techniques, where we try to develop algorithms based on how our data look like, minimizing possibly the assumptions and the a priori knowledge for the biology.
And would you say that it's one or the other? So is it either go for physiology-based approach or a data-driven approach?
Yeah.
Or is there an interface between the two?
Yeah, possibly many times we can distinguish these two based on how we build the mathematical process for devising the model. Of course, I am sure that many machine learning techniques, you need to incorporate some information. You need to take into account some information about what happens in your system. I mean, one would imagine that analyzing, let's say, data from the heart, it will be completely different from analyzing data from satellites.
Yeah.
So you need to customize your algorithm.
Yes.
So you are a modeler. You play an active role in this machine learning technique, but it let's say it reduces the way the mathematics are built for finally deriving the model for the analysis. However, although different in principles, I really strongly believe that these two things, physiology-based models and data-driven models, can come together, and I think that's the future of the analysis in medical imaging, combining these computational models that you can have, like pharmacokinetic analysis, with machine learning and image processing. And I think all these things need to come together and not to replace each other. And I think that's how we're going to maximize our efforts and our outcomes.
That's very interesting, because so my area of expertise, the area I work in, is to do with process modeling, and now there's a lot of data in healthcare, so there's a lot of data-driven process modeling. But I think that the future lies in combining qualitative data and quantitative data to make sense of what is going on.
Definitely.
So it's pretty much the same story.
Definitely, and I think the new supervisors in the field will realize this need, and so the new analysis people like you that you will come in the future will actually revolutionize with your hands-on work this field by combining
No pressure.
No pressure. No pressure. I think it won't happen in one day. It takes years most of the times for these things to give some results and convince the community. But I think it's really worth the effort.
So now that we've been very positive, so let's go to something less positive.
Mm-hmm.
I'm wondering what the challenges might be in reaching that potential. So what do you think the challenges are in medical image analysis nowadays?
I think being honest with your audience, I think one of the challenges is the fact that medical imaging data are not that available yet. So you need to be part of a medical imaging center, or you need to collaborate with a medical imaging center, which means many times that you need to have the time, the physical presence, and or the money.
Yeah.
And I think this will change by the new effort in the field. So I try again to be positive through this very obvious challenge that the people construct and structure online databases, which takes a while because I think this is analogous to the effort. It's very different acquiring images through a camera, and that just captures images and it's very easy. And it's very different to acquire images with an MRI scanner or a PET scanner.
Yeah.
People spend loads of effort. You can't imagine the amount of effort and the money that are spent for this.
Yeah.
So data ownership is one of the challenges. But people realize, because I think they see the previous generation of data in biomedical science, like molecular data and genetic data and all this stuff, and they saw how these were very well organized in databases, and this revolutionized the research there. And I think people in medical imaging see this example, and I believe there are more and more online databases towards this direction. And a very good example is here in UK. We have the UK Biobank,
yes,
which is an international example, I would say, that you see in conferences worldwide, that they mention the UK Biobank. And I think that's an amazing effort that has been done, and not only on the genetic and molecular data, but also on medical imaging data. I mean, the project that I said before that I'm starting on this summer is going to involve analysis from this.
Excellent.
Online. Well, it's not online because you have to spend a small amount of money to access the data, but it's a very good way to access existing data from people that they know that they will acquire images, and they will upload their data in UK Biobank.
Amazing.
That's one example,
yes,
possibly to stay positive.
It sounds positive to me.
Hopefully.
So I think the field is very exciting, and I'm pretty sure there will be some of our learners in this course interested in finding out more about medical imaging and medical image analysis. So what would you recommend to these people? Are there any conferences, any books, anything, anywhere that they could get more information about this area? Yeah,
there are many conferences in the field. I would mention two types of conferences. One is the MICI conference, which has to do with data analysis from medical images.
And it's called MICI.
MICI, yes.
MICI,
it's MICCAI. That's one of the very important conferences in medical image analysis and computing. And you can see data from all types of medical imaging, from MRI to PET to CT, everything. But of course, there is a very good national conference in UK called MIUA, MIUA, which also has international reach out. But also there are, I think, my advice, and many times I speak with modelers. My advice is to understand very well your data before start modeling your data. That's something that people are, the current generation of analysis people, of modelers, many times forget sometimes, I would say. It's very important to understand the data. So going to medical imaging conferences, not as a main task, but once in a while, to understand a little bit about the progress in medical imaging is quite important, because it will give you information about how you could analyze the images. So international societies of MRI and of PET are two very good examples of conferences for medical imaging. They obviously have loads of chapters in the framework of these conferences for computational physiology-based models that we discussed today. You can see loads of stuff. And because they saw the revolution of data analysis and of data science, they try to attract as well small venues of machine learning and all this stuff. So they try to combine. So perhaps combining MICAI and MUA, which are conferences for analysis, with medical imaging conferences, I think it's very good to see both. And of course, prioritizing depending on the work and on the priorities of the team.
And perhaps it's also worth mentioning that there are also lots of courses and programs available in medical imaging. So even the University of Edinburgh is running an online master's on imaging. So if you're really interested and want to get a special, get the skills needed to work in this area and the certification as well, that's one way to do it.
Absolutely, absolutely. Edinburgh Imaging and Edinburgh University have lots of online courses for these.
Excellent.
For these things.
Good. Anything else that you might want to share with our learners? Yours, Alex?
I would say give it a go. To keep it simple. I think the community has many open research questions for you to come and solve, to keep the enthusiasm level high.
Yeah. Excellent. Great. So on this very positive note, we'll say goodbye and see you in about a month's time in our next Hangout. Looking forward to the discussions in the forum. So we'll actually post the recommendations you made for conferences for you to have to look into if you would like. Great. Thank you and see you around.
Thank you.
Thank you.
Bye.
Bye.